This is problem 10-3.E, and it's on page 587. The beam shown in figure P10-3 carries a 6,000 pound load attached to a bracket below the beam. Compute the stress at points M and N where it is attached to the column. Okay, so quick sketch of what we've got here. There's a beam, sticks out from the wall a little bit. Point M and N. M is down here, N is up here. And basically we're not worried about this portion of the beam because it's larger, it's bolted, it's reinforced. We're not really interested in that part. The distance that we're interested in here is 52 inches. The load is attached at a point off center and it's got an angle. It's a 6,000 pound load. And it has an angle of 40 degrees. And there's a distance off the bottom of this beam of 6 inches. Now let's see, did they give us the overall height of the beam? Yeah, they did, because they told us that the beam is a W12 by 16. So let's go get the properties we'll need of that beam. And they've asked us to calculate the stress at those points. So we're going to need several properties. Let's see, W12 by 18, that's an I section, I-beam. Not too far, let's go back, there we go. Also a wide flange beam, that's what the W stands for. There we go, W shapes, page 700 and 701. Let's just jot down what we think we'll need. A 12 by 16, looks like it has an area of 4.71 square inches, a depth, which is this dimension. I'll just put it over here. A depth of 12 inches. Let's see. Elastic modulus, well, it's steel. What am I thinking? So elastic modulus would be 30 E6 psi, but I don't think we'll be interested in that because we're not comparing it to anything or calculating the deflection. Let's see, what else? Lost my place. Moment of inertia Ix equal to 103 inches to the fourth. And may as well get the section modulus, though we don't really need it while we're here. 17.1 cubic inches. Okay. So that should be all we need. Now, if we want to come up with the stress at M and N, how could we do that? Well, first of all, we'll have to solve for the reactions here, right? So let's take a free body diagram and figure out what the reactions would be. The first thing I'm going to do is break up the 6,000 pound force into two parts. This should be fairly simple. We call it a horizontal force and a vertical force. Okay? So the horizontal force and the vertical force, we should be able to calculate that easily. Sorry, I haven't worked this out ahead of time. You can follow along if you want. I would normally just include you guys, but I want to get this done quickly. So 6,000 times cosine of 40, and in degrees, gives us a horizontal load of 4,596.2 pounds force, and a vertical load, let's see, sine of 40 multiplied by 6,000, of 3,856.7 or so pounds force. I'm just going to round them off. Okay? Now, we have to have, obviously, a reaction load, F sub x, that is equal to F sub h, right? We have to have a vertical or a shear load, F sub y equal to Fv. But we also have to have a moment result, right? So notice that if we're summing moments about a point back here in order to calculate the moment in the material, well, the horizontal force is tending to rotate this way, but the vertical force is tending to rotate this way. Which one do you think is winning? Probably this one, right? How's that possible? This is a smaller load. Yeah, but look at the moment arm on it. This one has a small moment arm. This one has a very large moment arm. In fact, the moment arm for the horizontal force is is going to be half of 12 inches, so 6 inches plus 6 inches, so this will be 12 inches. But the moment arm for the vertical force is 52 inches. So obviously the vertical force is going to dominate, right? So the moment will end up having to be like this, because it's got to resist the twisting of this vertical force. So let's calculate the magnitude of that moment. So the moment would be equal to, excuse me, FV times, let's make this L. Well, forget it, we'll just put in numbers. So FV times 52 inches. Let's see if I want to take, well, we've already figured out the sign, so there's no point in taking a positive direction. So FV times 52 minus FH times 12. Okay, so let's plug this into our calculators. We've got numbers in the board, there's no point in making it more difficult. So FV times 52 less 12 times FH, 4596.2. I'm gonna put in the rounded off number here, but not the rounded off number there. Actually, you know what? I'll recalculate it. 6,000 times cosine 40, so that's easy enough. Cosine 40, so there we go. So I've got a moment of 145,394 and a half. You want that many decimal places. The units would be pound inches, or inch pound force of torque. So now we've got the moment back here. We've got all the loads, right? So we don't really care about what's going on over here anymore, because these are the loads within the material. Okay. So to highlight that, I'm going to just erase this, because I don't care about it anymore. It doesn't matter. I'm going to keep what beam we're talking about and the properties of that beam, but I don't need any of this anymore. In fact, I think what I'm going to do is recover this space and just draw the left-hand side face, which is what I'm interested in, noting that the moment is 145,300. Can I just round this off to 95? Is that okay? Inch-pounds force. And the force in the vertical direction is 3,856.7 pound force, and then the force in the horizontal direction is 4,596.2, and that's pounds force. Okay? Now, let me ask you a couple of questions. I know you're anxious to go, but let me ask you a couple of questions. What kind of stress will this moment cause? Normal stress, right? Will it be in compression or tension? Trick question, it's both, right? Because if the moment's acting like this, then it's pushing on the bottom. Let me put this in another color so you can indicate the stress. It's going to cause a normal stress like that and a normal stress like that. That's just from the moment. But FH is going to cause some normal stress across the entire surface like that, right? And FV, the vertical component, is going to cause shear like that, right? So we actually have multiple stresses to consider. Now we were asked to calculate the stress at M and N, and I actually wanted to extend this problem, but I don't really have the time. N was at the top, wasn't it? And yes. M was at the bottom? Okay. So if we're looking at N, we could draw a stress element like this. Now how much would the shear stress be? Okay, so if this face is this face, how much would the shear stress be? It's going to be 0, right? Because it's at the top, and we know that the shear at the top, if you look at shear equals VQ over IT, Q goes to 0 at the top and the bottom. And so since that's 0, that's 0. We don't have any shear on this thing, right? Instead, what we're going to have is sigma from bending, from the moment basically, and sigma from the direct stress, sigma D. And that's, we usually use that for design, so I don't know what to call that, but you get the idea hopefully, okay? There's going to be a similar addition of stresses on the other side, one from bending and one from the direct load. So how do we calculate that? Well, what we need, first of all, is to calculate the bending stress, which is MC over I. We've got all this stuff, it's not hard. 145,395 inch-pound force. C is going to be half the height, which was 6 inches. Remember the beam was 12 inches high. I, we looked up at 103 inches to the fourth. So plug that into your calculator, please. And we'll get the stress, sigma B, in PSI. Did you get this much? Okay, so there's the bending stress. What about the stress from the direct load from FH? Well, that's going to be 4,596.2 pounds force divided by an area of 4.71 inches. Good thing we got it. I thought we wouldn't need it. I forgot about this part. Okay. So 4,596.2 pounds force divided by 4.71 gives us a load, I'll just put it in here, of 975.8 or so PSI. So the total stress on this face, the total normal stress is the sum of those two. You guys can add that up easily enough, so I'm not going to bother doing it. Okay. What would happen down here at the bottom? You'd have to subtract it, right? Because look, the bending stress is in the opposite direction as the normal stress. In fact, notice that the bending stress is compressive and it's larger than this force, right? So what does that mean? Well, that means the compressive stress on the lower side is less than the tensile stress on the upper side, right? That's really important. Why is it important? Because that means that N is more critical than M, right? You really need to know that. You need to know where the critical point is located. You know, this is basically what they wanted us to do. We could also look at the center, and here's food for thought. As you move down, although the normal stress will decrease, the shear will increase. And then we're going to have a stress element that looks like this with, let's see, it would be something like this. And now we have to use more circle to add them together and find the maximum, right? Well, it turns out usually the shear is so small that as you move in towards the center of the beam, the combination of more circle gives you loads that are less than at the outer fibers. Okay, that's what usually happens. But in an I-beam like this, remember that the cross-section decreases all of a sudden, and so the shear shoots up. Even still, most of the time, the combination of the shear with the moment isn't bad enough. But what you can do is you can analyze, if you got an I-beam, like we have here, what you might want to do is not just analyze what's going on here and here, but what's going on here. Because that's the place where the shear is going to jump up all of a sudden, and the moment is still high because it's still far from the neutral axis. Okay, so sometimes you'll be asked to analyze that point rather than just the outer fiber. Okay? Questions, comments? All right, well, I wanted to extend this farther and actually do that, but I'm out of time. Thank you for your patience.